So good morning, everyone. My name is Michael Upchurch. Up here with me today are Elizabeth, Keith, and Kelsey, and we will be presenting to you on behalf of the Valparaiso Robotic Football R&D team. As a brief overview, we will begin with our project goals, which will lead us to the design. More specifically, we will talk about the design of each of our 4 different subsystems. Then, we will show you some of our game day results, talk about some of the testing and validation, some of the challenges we faced, some things we would have changed in the future, and also the lessons we learned throughout the project. Our main project goal was to design and build a robot to play the center position in the robotic football competition. More specifically, our robot needed to be able to hand off the ball successfully in 3 different positions. And it also needed to provide a high torque and pushing power for the maximum possible blocking. As I stated before, our project had 4 main subsystems. The first being the handoff mechanism, which was responsible for delivering the football to either the quarterback or the running back. Next was the control system, which powered our project as well as told it what to do. Next was the frame, which protected and was the housing for the control system. And last was the drivetrain, which allowed our robot to be driven in any direction. I'm going to go a little bit more in depth to the control system now. So we had a 12-volt battery which powered the entire system. And for the brains of our robot, we had the Arduino Mega ADK. Now the user would use a PlayStation 3 controller, and they would push a button or move an analog stick, and the Arduino would recognize what they did and then send a signal to one of our various components. It would talk to the Victor in order to get the motors to rotate, and it also talked to many different servos in order to move the handoff, drop the ball, be able to place the ball again. But in order for the servos to work correctly, we needed to go from the 12-volt battery to a 12-volt to 5-volt converter. Without that converter, our servos would not work properly. Another thing we had was our LED strip. So in order to power this LED strip, it had a 12-volt line, and then also we needed 3 different MOSFETs for each of the 3 different colors. Now the first pin on each of the MOSFETs was a control line, so that would go to a different pin on the Arduino. The middle pin of each was the color that we wanted to turn on, whether it was red, green, or blue. And then the last pin for each of those was grounded. So for the controller layout, the different inputs you could do were you could use the left analog stick to drive the robot forward or backward. You could use the right analog stick to steer it left or right. R1 would engage the ratchet system to make it harder for it to be pushed back, and L1 would disengage the ratchet system. Now you could hit square, cross, or circle to move the handoff to your desired position. You could hit the L2 button to drop the football, and you could hit the triangle button to move the gate back up so that you could replace the football there. And so if there were any reason that our rotating servo for the handoff mechanism got knocked off of alignment during the game and the square, circle, or cross button was not putting the handoff mechanism to its desired location, we also added a fine-tuning mode on left or right push buttons on the D-pad, so that if you push left or right, it would move the handoff mechanism 1 degree in that direction until it reached its desired location. And next is Elizabeth.
So for our handoff mechanism, we had 2 requirements. It had to be multi-directional to allow for more advanced strategy and trick plays, and it also had to securely hand off the football. The ball was supported by 2 gates, which are mounted to the larger rail bracket and powered by a servo through a series of gears. When the gates were released, the ball would roll down the polycarbonate ramps into the receiving robot. The smaller rail bracket supported the end of the ramps and is housed in a arced slot in the handoff plate. This mechanism was turned by a servo located underneath the handoff plate, and the whole system was attached to the lid by 3 support columns. For the frame, as the game rules required, the base plate was made of half-inch thick HDPE and edged by a bumper. It also had to be serviceable for quick repairs during game. The shape of the frame was octagonal, which allowed the receiving robot room to get close to the back of the robot for the handoff positions, and left the front with a wedge-shaped nose to push through the opponent's line. LEDs followed the circumference of the wall, and the number 68 were posted on 3 different panels, which means that the LEDs and numbers could be seen from any angle of the robot. The battery is mounted in the center of the robot and fastened by a winch strap with a quick release system for easy changing of the battery. The lid was partitioned into 2 halves and hinged at the center of the robot. The back half housed the handoff mechanism and is attached to the frame by 3 screws with wing nuts. The wing nuts can be loosened by hand and to allow removal of the lid and access to the Arduino. The front half of the lid was latched to the front nose panel and could open up to 90 degrees to allow access to the battery. For the drivetrain, there were 3 requirements. It had to have a high pushing capability, had to be serviceable, and it had to be maneuverable. We used 2 low diameter Bainbots wheels on each motor to provide the grip necessary to push the opponents. These center drive wheels allowed for precise movements. We used 2 mini sim motors paired with planetary gearboxes. These gearboxes transformed the power from the motors from speed into torque. Plasma cut plates were housed between the motors and gearboxes and attached to aluminum blocks which were bolted to the underside of the base plate. Another part of our drivetrain is the ratchet system. This consists of a servo-actuated lock bar which, when engaged, allows the lock bar to fall into the teeth of the hub attached to the wheels. This allows free forward movement but prevents the robot from being back-driven. As you can see in this video, our robot, when the ratchet system is engaged, the other robot spins its wheels in effort to budge the center. As for our game day results, you can see from this video that our robot has the power to push through the line and sack the quarterback.
So we had to have our robot ready a bit earlier than most of the other projects because the competition was on April 8th. So beforehand we did a bunch of practical testing, just making sure that things would actually work the way we wanted them to. And then after, we wanted to get some more scientific testing to quantify the different variables of our robot that we cared about so we could have some performance metrics to tell people about. So the first test we did was to figure out the top speed of the robot. So we just had a tape measure on the floor, measured out 20 feet, we ran it 5 times down at its top speed and just recorded the time. And we found out that our average top speed was about 3 miles an hour. The second test we did was to determine impact resistance. So we wanted to know if it could survive the on-field impacts it was going to be experiencing pretty frequently as a lineman on the field. So we drove it at top speed into a wall 10 times and just checked to make sure that it worked afterwards. So we would just back it up after it hit, and we tested to make sure the handoff worked fine, that the ratchet gear could still be engaged, that you could still drive it. Just made sure everything was functioning and that nothing was broken. And we just recorded the success or failure of the 10 trials, and we found out that it's pretty tough. It didn't break at all the whole time. The next test we did was to determine the security and reliability of our handoff mechanism. This was just because we wanted to know how reliable it would be during the game, so that we could see if there were going to be any fumbles, if it was going to be on us, or if it was due to another robot, so that we could account for what we could control. And we did 20 handoffs for each position, the left, the back, the center, and the right. And we just recorded whether it successfully made it to the quarterback arm in a position where it could be thrown, or securely into the running back's net. And we just recorded the success or failure. And it didn't fail at all. It worked perfectly every single time. So we were able to assume that it's a very reliable mechanism, and that if there's any fumbling, it's not due to the functioning of our robot, but more so to one of the others on the field. The fourth test that we did was to put a number on how strong the robot was. We wanted to know how much it could push. So this was important because as a lineman, it's going to be either blocking, or whether run blocking to push through the line, or pass blocking to keep somebody back, or on the defensive line, it's trying to push its way through to get to the quarterback. And so we wanted to have a number for that. So we attached a spring gauge to the robot and to a stool that someone was sitting on, so that it was essentially a fixed object, and we just drove it forward and recorded the force. And I think we did 10 trials and averaged that, and we found that it could exert about 17.5 pounds of force against an opponent, which is significant because it's about 25% more pushing power than the previous center was capable of. So it's quite an improvement on the design. And then the final test we did was to determine its pushing resistance. So this is important specifically for pass blocking, to see if we could keep it stationary, not let any other robots get past. So we did a similar test. We hooked the spring gauge to the robot, but this time we didn't drive it at all. And one of the team members just pulled on the gauge until the robot started to slide forward. And we would just record the force from that, and we did 10 trials again and averaged the values, and we did it without the ratchet engaged and with the ratchet engaged to determine just how effective that system was. And we found that without the ratchet engaged, it could only resist about 4.5 pounds of force. But if you engage the ratchet, it could hold up to 11.3 pounds of force, which is significant because there's not a lot of other robots that are capable of pushing that much. So it means we could resist the vast majority of ones that we see on the field. And it's also significant because it's 150% more push resistant than the previous center, which is a very, very large improvement, which helped our passing game quite a bit.
So we ran into a couple challenges over the semester, one of which is the traction of our wheels. In the beginning, we chose the Vex traction wheels. These Vex traction wheels we chose these because of their high modular design, and they were specifically designed to mesh with our gearbox. So the reason why we decided to move away from these was these were designed for carpet, much like we're standing on now, and start slipping and sliding when you get onto the wood play surface, which we realized after starting to practice with the robot. So we moved on and started looking at different wheels. The first of which we looked at were the Andy Mark wheels you see there. These are very interesting because they actually deform under weight, kind of giving you a plane instead of a point of traction, which gives you a lot more force to the ground. And the one problem we had with these wheels, although having a high amount of traction, they do start falling apart after use. So after just 1 hour of playing, they started to disintegrate. So we had to come up with another alternative which were the main butt wheels, which was our final choice. These wheels will have both the high traction that we desired. These high traction also paired with the fact that they were machinable. Now, the machinability allowed us to actually use these and combine the benefits of the Vex wheels, so getting best of both worlds, because we could create a modular design. Another challenge we ran into was the motor stability. We didn't notice this before because we were getting so little traction with the old drive wheels, but with the new drive wheels, we were actually, when producing so much torque on the ground, we were actually breaking the old motor mounts. To counteract that, as Ellie talked about, we made a plasma cup part with a aluminum mounting block. This gave us a more secure mounting system because the mounts were in between both the gearbox and the motor, which we could then tighten down the gearbox to that motor plate. In addition to that, we had 4 mounting points instead of the 2 from the previous design. One of the other challenges we ran into was actually the battery. The battery is the heaviest component in our robot. It is, so the security of it is very important. We had to, in our original design, it was secured with Velcro, and with that weight, the Velcro actually started to slip and would break loose. So instead, we added some more bracing in the back, as you can see there in that picture, but we also added the ratchet straps you can see there, providing us the same quick access as the original design, but added a very much more secure system. So for our future improvements, we would suggest to have a work on the wire manager for this robot. We've had some problems with the LED reliability, and this is just this way these specific LEDs interact. So we would suggest looking into how different LEDs would play into account, take into account. We'd also suggest for the next users of these robots, for this specific robot, to adjust the control scheme of the PS3 controller for their actual wants. In addition to this, for aesthetic reasons, we would want to print all of our parts in one singular color, which would allow us to have a more aesthetically pleasing part. As of lessons learned and applicable stuff that we learned from this project to our future career was the benefit of working early and often. Because of our accelerated schedule, we did have to do a lot of early accelerated schedule. Sticking to a plan was also something we learned. But with this early and often mentality, we actually started to we could benefit from an iterative design. The iterative design meaning we can start early and discover those challenges before we even had to use the robot in more of a professional manner. Another thing that we learned was the communication is key between the electrical and mechanical team members. Due to the way our robot works, we had to design these parts simultaneously, and it would be better to have them integrated all at once in the end. So, in summary, we talked about the project goals, the designs we came up with, and our final design. Then we went through how we performed in the game, We went through the testing and validations, the challenges, and the lessons learned. Thank you. Any questions?
So in the competition, you guys lost.
Yes.
So I don't mean that in the bad.
Yeah, no, it's okay.
I guess my question is, what would you have done different? Like, what did the opposing team do? And was it these robots that were like affected the results, or like how would you have done better in the competition?
Better in the competition. A lot more practice. Driver practice was key to what we were trying to do. Some of the, specifically for our driving, Ellie can contest to this. She was the driver of the center. We needed to be able to line up that four-way so that the quarterback and the center. So the one thing we really suggest is more practice between the driver and the two multiple drivers on the team.
So like everyone's got a separate controller,
Yeah.
like coordination.
Coordination between the robots and practicing those plays was also pretty important too.
Do you think like your robots were on the same level as like the opposing team? So it was just all practice, or was there some?
No,
technical-
there was definitely some technical side. Some of our robots were very competitive with theirs. I don't think any of their robots can outpush us. I don't think we had any problem in game pushing around any of the robots, ours specifically. But there were their robots, their running back. I don't know if anybody saw the game, but their running back was really fast. And our running back was not competitive enough with their robot to catch up to them, although they're working on it.
Go back to those testing slides that keep
Which one?
the next one. See that?
Yeah.
Yes. Okay. So on the very bottom one, it said 150% more push resistant. Is that the 4.5 or the 11.3?
That is the 11.3 in comparison to the original center.
So that they had 8 pounds force before
I believe
last
so.
year. Okay. Then I'm just wondering if it was 8 last year, then we came up with 4.5. So without the ratchet, we got 4.5 pounds force pushing resistance, and last year they had 8. So it's great with the ratchet, we overcame last year, but then what was the difference between last year we had 8 and this year without the ratchet, 4.5?
I believe they had, I'm not quite sure on the numbers of the original design, or on their design. I believe it was actually closer to 5 pounds, although that percent difference would make sense. Looks like-
Okay, so maybe the 150% more is actually 250% of?
Maybe. Ethan's pointing back at me.
We did this test with the old one, and its pushing resistance was 1.5 pound force.
Okay. Well, and then maybe the ultimate question is, if we put our center this year and our center and last year's center, push them against each other and so forth, would ours have won?
That was the
Yes.
video. that
This
you
one would
saw.
definitely win.
Okay.
Yeah, the video that was playing.
I was just trying to make sense of the numbers.
This one is, this video is of our old center, Robotic's old center, and our current center. If you watch this video, and it's a lot clearer in the.
Yeah, one's them pushing us and then us pushing them.
Yeah,
But, so you use, I'm trying to get off on this, but you said last year was 5. 5 years with 5 pounds force resistance? 1.5
So 150% was the 4.5.
was the 4.5.
Yes.
Oh, okay. No, that makes
kind
sense.
of.
Okay. Did I,
Been done numbers lately.
did you say that at the beginning and I misunderstood?
I don't think we would.
Okay.
I'm assuming.
All right. Go back to the slides. I think the one before it then. Any question? Let's see.
That one, or doesn't?
Handoff, okay, next. And then, what was it, pushing? Oh yeah, this was one. Okay, and this was that thing about the head-to-head, right?
Yes.
So this is like delta force. Special forces team, but this is the change in force, right? So we could push basically 7.5 pounds force more than the other robot. Is that right?
No, that was what we produced. It was-
Okay, so that's just total with the spring gauge?
Yeah.
Okay. And then, but I remember one of the tests we were gonna do was basically a head-to-head.
Right, but we couldn't get a number with that. Like you could very easily, you could do it and see it, but
It's
like
in the
if you
video.
wanted to, yeah, it's in the video. Like we've done it, but if you
Alright,
wanted a number,
I guess that
it
was-
wouldn't work because we didn't have the measurements.
So this isn't, we had 17.5 pounds more than the other robot.
Yeah, so if you
just
were
held the spring scale, pushed forward, we got 17
Yeah.
pounds.
So if you were curious in that, you could just do the same test with the other robot and then subtract,
And which
and then
we
take
did
the difference.
do, and that's where this new number came from.
Yeah.
Oh, okay. So if that's 25 or 75, it seems terribly long. So they had about 14 pounds of, so the other robot would have had 14 pounds.
Roughly. Yeah.
That's it.
Great, thank you.